What's up? What's up? It's your man Jimmy Chan. All right, so we are talking about the properties of rational functions. And guys, don't forget, rational just means fractions, right? So we are talking about functions that are in fraction form. That means there is a numerator, a denominator, a top, a bottom, right? So what do we know about fractions? We know that the denominator cannot equal to 0 because then the fraction's undefined, right? If x is real, then the domain would be x is cannot be that. Meaning if the denominator, whatever makes the denominator 0, x cannot be that value, okay? And if it's imaginary, then we don't have to worry about it being, because then the restriction is actually imaginary, which is a life lesson by itself, right? The graph of the rational functions never intersects the vertical asymptote, so it can never cross the vertical asymptote, all right? So let's talk about vertical asymptotes versus holes, right? So again, at the restrictions, those x values make the fraction undefined, but some of them will be a vertical asymptote, so it's pretty obviously where it cannot cross. And then there is going to be some that are not vertical asymptotes, but there's going to exist a hole because, again, the x value cannot be that value, okay? So let's take a look. You can certainly read this yourself, but let's go ahead and do an example so I can actually show you what that means. So one of the things that we want to do is always to factor the top and bottom. So if I factor this, g of x is going to equal to, the top is going to factor out because that's the difference of two squares. So that's going to be an x minus 5 times an x plus 5. The bottom there is going to be an x minus 5 and an x plus 7. There we go. All right. And if we checked, negative 5 times 7 gives me negative 35. Outer is positive 7. Inner, negative 5. Adds up to a positive 2. Okay. So with that being said, see how that if I was to reduce this fraction, that these two would cancel. Is that right? Since these two cancels, first of all, I can say x minus 5 cannot equal to 0. So x cannot equal to 5. So, but since they cancel, I don't have a vertical asymptote here. I'm going to have a hole at x equals 5. Okay? So that's what's going to be the case because it cancels. All right? So let's put that right there. There we go. And since here the 7, the x plus 7 doesn't cancel, right? So I got x plus 7 cannot equal to 0, so x cannot be negative 7. That means I have a vertical asymptote because it doesn't cancel at x equal to 7. Now, just so you guys know, the top information here of this line is more about the domain. Okay, so when I talk about the domain, I can say that x cannot equal to 5, x cannot equal to 7. So that's mostly about the domain. What's happening with the graph is on the bottom, that there's going to be a hole at 5, and there is going to be a vertical asymptote at x equals 7. So that's how we determine if it's going to be a vertical asymptote or if it's going to be a hole. All depends on if they do cross out or if they don't. Okay? Because if I do cross these out, what's the g of x going to end up being? Well, the g of x is going to end up being really x plus 5 over x plus 7. Right? So here, if you look at the reduced or the lowest terms of the fraction, you're not going to see the x minus 5 anymore. Right? But you're definitely going to see the x plus 7, so the vertical asymptote is obviously going to be there. And that's why there's a hole there. It's because the x minus 5 cancels out, so you don't really see it, but there is actually a hole right there. Okay? Just because we cancel it out doesn't necessarily it never existed. Okay? All right. Let's get to the next example here. Let's talk. Oh, I can't move that. Okay. So now let's talk about, so we just talked about vertical asymptote and holes. Now we're going to talk about horizontal asymptotes. Okay? Horizontal asymptote is where we compare the power of the largest term on top and the largest term on the bottom. We're comparing their powers. Okay? So notice the m and the n. All right? So this is assuming that the ax to the m is the largest powered term on the top, and bx to the n is the largest powered term on the bottom. Now, I don't know how many terms there are, but these two are the big ones. All right? So here's the thing. If the power on top is greater than the power on the bottom, then there's no horizontal asymptote. Meaning, if I was to compare two powers and the powers were, let's say, 2x to the third over 3x squared, right? So since 3 is greater than 2, then no horizontal asymptote. Okay? Now, if the power on the top is less than the power on the bottom, then there's a horizontal asymptote at y equals 0. So if I had 3x squared over 2x to the third, since 2 is less than 3, then we have a horizontal asymptote at y equals 0. And then last but not least, what if they were equal? Okay, so let's say I had 3x squared over 2x squared. Since they're the same, since 2 is equal to 2, then my horizontal asymptote would be the ratio of the 3 over the 2, which is the ratio of the coefficient. Okay? So those are the three cases. So a horizontal asymptote, so in a horizontal asymptote, you can cross it, the graph can cross it many times. However, the horizontal asymptote is talking about the end behavior, what's happening towards the end. All right, so if I had a horizontal asymptote right here, my graph could cross it many times, but what is actually happening at the end behavior, right? The end behavior is slowly getting closer and closer to it, okay? So that is what it really is about, all right? All right. So let's talk about oblique. Oblique, we're still comparing the largest power on top with the largest power on the bottom. However, the only time you're going to have an oblique is if m, the power on top, is greater than n by 1 degree. Okay? Only by 1 degree. If it's more than 1 degree, no good. It can only be 1 degree. Meaning, for example, if I had 2x to the third over 3x squared, that's okay. I have an oblique asymptote. But if it's like 2x to the fourth over 3x squared, then I don't have an oblique anymore. Okay? So it can only be more than 1. So if it wasn't a 2 here and it was a 3, then again, we're back to oblique. Okay? So the power can only be, on top has to be only 1 greater than the bottom. This is called the oblique asymptote, which is also called a slant asymptote, or a slant, okay? And yes, same thing as the horizontal asymptote. It can cross a bunch of times, but it's really going to be the end behavior of the oblique asymptote as well. It can cross many times, but the end behavior is going to eventually get there. And yes, the only way that we get there is to find it by long division. All right? Okay, so let's do an example here. So it wants me to find the horizontal asymptote here and the oblique asymptote, or the oblique asymptote. Okay? So for horizontal asymptote, okay? So if we look at this, we're going to compare the largest power on top, which is 3x to the fourth, with the largest power on the bottom, which is x to the third, and the power on top is greater than the power on the bottom. If that is the case, we have no horizontal asymptote. Okay? The only time we do is when the power on top is less than the power on the bottom, or the power on top is the same as the power on the bottom. Okay? However, we do have an oblique asymptote. Okay? We have an oblique asymptote because the power on top is only one more. It's only one more than the power on the bottom. So I don't know if I should say, since 4 is equal to 3 plus 1, or should I say that 4 minus 1 is equal to 3, right? So then that's again talking about the power. Okay? Or the exponent. So there is one. So in order for me to find it, okay, so there is one. So how do we find it? We actually have to do long division. So we'll have to do x to the third minus x squared plus 1. And this is the reason why I'm showing you guys long division all along, is because I can't do synthetic division here. Okay? So, how many times does x to the third go to 3x to the fourth? 3x times. Whoa, this makes it very easy. Actually, 3x I should probably put all the way over here. And then when I multiply, what do I get? I get 3x to the fourth minus 3x to the third plus 3. Ooh, I forgot the space holder for this. There we go. So this would be plus 0x squared plus 3x. There we go. That's better. So then we got to flip all the signs and add. So that goes away. I get a 3x to the third minus x squared minus 3x, and then bring down the last term, which is plus 0. How many times does x to the third go into 3x to the third? That would be 3 times. So let's multiply. I get 3x to the third. Let me see. Minus 3x squared plus 0x plus 3. Flip the signs and add. Then I'm left with a 2x squared minus 3x minus 3. Okay? So, my oblique asymptote is going to be at y equals 3x plus 3. All right? So that is where the oblique asymptote is going to be. So no horizontal, but there is oblique. Now, the question is there going to be a way that the graph is going to touch this? Okay? So that is the ultimate question, right? is the graph going to intersect the oblique asymptote? Okay, so let's take a look. The only way we know, because this is y equals, is that right? This is y equals, is that right? Okay, so the remainder doesn't really matter. Okay, it's about this part right here. So this is a y and this is a y, let's set them equal to each other. So question is, when is 3x plus 3 going to equal to 3x to the fourth minus x squared over x to the third minus x squared plus 1? Okay, so the question is, when are these two equal to each other? So since I have a single fraction over a single fraction, this is where you can use cross multiplication. So if I cross multiply, I get times, and that's going to equal to, so let's see what happens here. I have no idea what's going to happen. Let's see what happens. So I got 3x to the fourth minus 3x to the third plus 3x to the third minus 3x squared plus 4. Okay, so this side is going to be 3x to the fourth. The x to the third goes away. I got minus 3x squared plus 3x plus 4 is equal to 3x to the fourth minus x squared. So let's get everything to one side. And what do I have here? 3x to the fourth goes away. Add the x squared. If I add the x squared, I get, oh, I guess I want to move everything to the right. So I'm going to have 0 is equal to 2x squared minus 3x minus 4. So is this factorable? Let's see. Yeah, the 2 and 4. No. Can't do 4 and 1, 1 and 4, no. 2 and 2, no. So this is not factorable, so I'm going to have to try the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. What is my discriminant here? That is going to be a 16 times 2. All right, 16 times 2 is 32, so 9 plus 32 is 41. So this is going to be x is equal to 3 plus or minus the square root of 41 over 4. So this is going to, it is going to cross it, but at those 2 points, right? So if I had to do it by, let's see here, if I was to plug that in, fraction, 3 plus square root of 41 over 4, that's going to be about 2.35, and then if I subtract it, it's going to be negative 0.85. So around the x values is where it will cross that horizontal asymptote, right? So I can actually calculate where it is going to cross, all right? So that is the way you would go ahead and do that. I know it seems like a long process, but again, the long division doesn't seem like very difficult because it's pretty short, right? It's 2 lines and it's done. But is it always going to ask you if it's going to intersect? Well, only if you're going to be graphing rational functions, if you're going to be curious of if it crosses the oblique asymptote. Now, if there's a horizontal asymptote and no oblique, then it's going to ask you if it crosses the horizontal asymptote. All right. Well, I hope everything is good. Have any questions, please let me know. See ya. Bye.